Welcome to the 7th session of Geometrical Properties of Section in Engineering Mechanics and Strength of Materials. In the 7th session, we are going to learn the theorem of parallel axis and we are going to find out the moment of inertia of the different lamina including square, rectangle, hollow rectangle, circle. Now we are going to deal with the theorem of parallel axis. In this theorem of parallel axis, first we are going to consider a lamina. In the given lamina, we are going to mark the centroid and we are going to place the x axis. In the whole lamina, we are going to consider a strip. By that, we can find out the total area of the plane area. With respect to the x axis, at a certain distance apart, we are going to consider the AB axis, which is parallel to the x axis. The considered strip of the lamina is y distance apart from the x axis and AB axis is h distance apart from the x axis. In the theorem of parallel axis, it states that the moment of inertia of a plane area about AB axis is equal to the sum of the moment of inertia about the x axis and product of the area of the lamina square of the distance between them, and the statement is given in the equation format, that is moment of inertia about AB axis is equal to the moment of inertia about the x axis of the given lamina plus area of the lamina multiplied by the distance of the AB axis with respect to the x axis square. Here the moment of inertia about the AB is measured by millimeter power 4. The moment of inertia of the given x axis is millimeter power 4 and the area is measured millimeter square, and h is the distance between the center of gravity of the section to the axis AB, which is in millimeter. Now let's move on to the moment of inertia of the lamina. To find out the moment of inertia of the square lamina, in the given square, the width of the square is b and the depth is also b. We have given a reference axis as xx and yy. Since it is symmetrical about both the axes, the ixx, that is the moment of inertia about x axis, and yy axis is b power 4 divided by 12, where width is a b. And if we consider this x axis at the base of the square lamina, then the moment of inertia is going to change as the moment of inertia about the base is nothing but b power 4 divided by 3. Now let us consider the rectangular lamina. In a rectangular lamina, the width of the rectangle is b, so that is a small b, and the depth of the rectangle is d, and it is also symmetrical about xx as well as yy axis. To find out the moment of inertia about x axis in a rectangular lamina, it is b d cube divided by 12. And if we find out the moment of inertia about the yy axis, it is d b cube divided by 12. Here width multiplied by depth cube divided by 12. Here in a yy axis, depth multiplied by the width cube divided by 12. And if we consider the zz axis, it is the addition of xx axis and yy axis. That is izz is nothing but moment of inertia along x axis and moment of inertia along y axis. Here it is a bd cube by 12 plus db cube by 12. If we take common as a d and b, it's a bd divided by 12, b square plus d square. And if we consider the moment of inertia at the base of the rectangular lamina is nothing but bd cube by 3. the moment of inertia about the base of the rectangular lamina. If we consider the x-axis at the bottom of the rectangular lamina. Let's move on to the rectangular hollow section. In the given hollow section, the width of the exterior rectangle is caps B and the depth is caps D, and the interior section is nothing but small b and the depth is small d. Here, if you need to find out the moment of inertia of the given section is nothing but b d cube by 12. Within that, we have to remove the removed portion of the rectangle, that is b d cube by 12. The interior dimensions are small b and small d, and as well as along the y axis, if we are going to find out the moment of inertia in a rectangular hollow section, it is d b cube divided by 12, as well as in an interior hollow section, it's a d b cube divided by 12. Now let's move on to the circular lamina. Here we have a circle and it is having a diameter d. It is symmetrical about both the x-axis as well as y axis. Therefore, the moment of inertia along x axis and y axis, it is pi d power 4 by 64. And if you are going to find out the moment of inertia along the z axis, that is a zz axis, it is moment of inertia along x axis plus moment of inertia along y axis. It is 2 times pi d power 4 by 64. So 2 is 64 divided by d power 4 by 32. Now let's move on to the hollow circular section. In this hollow circular section, it is same as that of the rectangular section, where the exterior diameter is caps D and the interior diameter is small d. Within that, if we need to find out the moment of inertia, is nothing but x-axis and y axis is same, which is pi caps d power 4 divided by 64 minus pi caps d power, so small d power 4 divided by 64. Within that, we have taken pi by 64 as a common, caps d power 4 minus small d power 4, where caps d power 4 is the external diameter of the circle and small d is the internal diameter of the circle. Therefore, hollow circular section, the formula of moment of inertia is pi by 64 d power 4 minus small d power 4. Now move on to the triangle. In the triangle, if we are going to consider a triangle where the top of the triangle axis is AA, let us consider this one, and XX is at the center of gravity of the triangle and BB is the bottom base of the triangle. Here the centroidal distance is 2/3 of h from the apex of the triangle, and from the base it is 1/3 of h. And if we are going to find out the moment of inertia about apex of the triangle, that is IAA, is bh cube divided by 12. At the apex, if we are going to find out the moment of inertia, the formula for that is bh cube divided by 12. And if we are going to find out at the x axis, which is going to move at the centroid of the triangle, that is bh cube by 36. And if we are going to find out the moment of inertia at the base of the triangle, that is bh cube divided by 4. Now coming to the channel section. If you are going to consider the channel section of depth caps D and width caps B, and the removed portion is small b and the depth is small d. Here it is having a overall thickness of t. If we consider this channel section as a whole rectangle, that is b multiplied by the d, within that small b multiplied by the small depth is removed portion, then we can easily find out the moment of inertia along x axis because it is symmetrical about the x axis. Therefore, it is a bd cube by 12 minus small bd cube by 12, by considering this channel section as a rectangular channel section. Within that, this rectangular portion is removed. The same formula is going to apply for the I section. The width of the I section is caps B and the total depth is caps D. Within that, a smaller portion of small depth with a b by 2 and again small b by 2 with a depth is removed. And if you look at the I section, you can easily see that in the I section, if you move this web to the end of the I section, then it is going to look like a channel section. Therefore, here also the same formula is going to apply. Ix is nothing but bd cube by 12 minus small bd cube by 12. And for the y axis, it is symmetrical about y axis. Therefore, it's a 2 time moment of inertia of the first flange where the corresponding y axis plus moment of inertia of the web where corresponding axis is y. Here we have some multiple choice question for the moment of inertia. The moment of inertia of a square cross section side A about diagonal is a power 4 by 3, a power 4 by 8, a power 4 by 6 and a power 4 by 12. Of course, the answer is D, that is a power 4 by 12. Here in a second question, the moment of inertia of a circular section about an axis of the section is pi d cube by 32. For the circular section, actually it is a pi d power 4 by 64. Therefore, the answer is B, pi d power 4 by 64. In a third multiple choice question, the polar moment of inertia of a circular section is about x-axis, y axis, z axis and neutral axis. Of course, it is a z axis. In a moment of inertia of a rectangular of base B and depth D, about the base will be bd square by 6, bd cube by 12, bd cube by 3. Of course, the answer is D, is a bd cube by 3. Thank you.